until your next exam. So 9 more classes until your next exam. Then we'll have, I think, 2 classes, and then we'll have your final. So 9 more classes.
I think it's 3, Friday, Monday, Wednesday.
I think we're not going to meet Wednesday. So I think it's 2. Right?
This Wednesday?
Okay, so
You should really
No,
go
for the
over
final.
yours.
What's up?
If you have time for review, I
Yeah.
might show up.
We may. That's why we may do that on Wednesday. The very last day, the 6th, December 6th. That's why I think we're going to say we're not having class that day, and I think we're going to have a review. What's up? Someone is, and I posted them today, this morning. So they're on Echo. They're up. I promise you. They're up. They're up on Echo today, this morning. They may not be up yet. They're uploading. They're not up at the moment. They're at least uploading. I've initiated everything. They're going. What's up?
Does the thingy work now?
The thingy.
Yeah.
Echo.
Thank you.
No.
The Echo thingy.
Echo's still not working. On Ulrich's recording, he gave me all the files on Friday. I put them on Echo, but I didn't upload them to your class. I uploaded them to your class this morning, so they're on your Echo. I also uploaded them to the Tuesday, Thursday class. Because you guys are so generous. They're complaining about your class? Oh, that's why you're taking your next exam on Wednesday. That's right. No, not because they're complaining, because you're taking it. Okay, so today we're going to finish all the content up until glycolysis. So we're going to finish talking about bioenergetics. We're going to talk a little bit about metabolism. The very, very generic brief overview of metabolism. I'm going to give you some terms. Hello. Whose phone is this? Oh, you just put it up there? What app is this?
It's Recorder.
Recorder.
It's great.
It's what?
It's great.
It's great. It has a nice looking 80s cassette tape on it. Looks nice. Okay. So we talked about, the last thing we talked about, the idea of our lecture on last week was that many biological processes are unfavorable, and how do we get over unfavorable energies? How do we overcome unfavorable barriers in biochemical reactions? We talked about 2 ways we overcome a positive delta G naught. First is removal of product. Concentration has an effect. We remove product, we drive equilibrium towards products. So even if they're favorable, we can, in certain situations, overcome a positive delta G simply by the fact that it's in the middle of a metabolic pathway or a large stepwise biochemical process. If we're taking product away, we're going to continue to drive the reaction towards products, even though it's inefficient. Second was that many of these biochemical processes and biochemical reactions are coupled. They are coupled with favorable interactions. We talked about one favorable interaction. We said the hydrolysis of ATP was a very favorable interaction. We talked about hydrolysis of ATP. We drew a reaction mechanism for the hydrolysis of ATP. We talked about hydrolysis of various forms of hydrolysis of ATP, right? ATP can produce phosphoryl transfer at the gamma phosphate. It can produce it at the beta phosphate, alpha phosphate. What else did we talk about? Oh, we also said one thing that isn't really correct. We said this was a coupled reaction, right? We said many unfavorable biochemical reactions are coupled with favorable reactions, things like ATP hydrolysis. They are coupled with things like ATP hydrolysis. The hydrolysis of ATP isn't really the favorable part. It's the transfer of the phosphoryl group. That is the favorable part. So if it's not hydrolysis of ATP, if it's really if what we're really concerned with is not necessarily hydrolysis of ATP, but the actual transfer of that phosphoryl group, one thing we need to take into account is that ATP, AMP are not the only favorable phosphoryl transfers that we have. If you look in your textbook, you'll see a long list of some of them that are even higher energy, some of them that are less energy. So we are going to answer 4 questions, and we're not going to do number 5. I don't feel like talking about it. It's not really very necessary. It doesn't talk about it in, I think, either of your textbooks, so we're going to leave that. sort of explanations can we give for the large delta G? I guess we should probably say delta G naught value, right? We're talking about things, all of these values we were talking about before, the delta G naught values, or the standard state free energy change values. So what are some factors that play into this large negative standard state free energy change for the ATP of hydrolysis? What does the literature book talk much about this? I don't think it does. The literature book doesn't do a very good job talking about this. The Biochem book does a much better job. I think the Biochem book talks about 3 of these, maybe even 4 of these. 3 of these, to some degree. First thing that we're going to talk about is negative or electrostatic repulsion or electrostatic interactions. I shouldn't say that. I'm going to say unfavorable. It's kind of the same thing as repulsion, right? Repulsion factors, unfavorable repulsion. Repulsion. And I didn't want to say negative. Why? Because it's actually too positive. What's positive? That's negative repulsion. If we draw this, let's draw ATP. I'm going to draw it a little different. Protein effect. No, talk about why. I shouldn't have. So. And there are my 2 phosphates, and I'm left with another phosphated density. So I'm just AMP, right? Our shorthand version for ATP, we have AMP and 2 phosphates, that's ATP, right? Mono, di, triphosphate. So here's my shorthand for ATP. We look at what are some factors explaining favorable delta G values, the hydrolysis of ATP. If we finish our reaction and hydrolyze this, we are left with an inorganic phosphate. EP. Inorganic phosphate, I guess, is the hydrogen. Reaction that we do last week. So the first thing we're going to talk about is relieving unfavorable repulsion. We talked yesterday about charge. What is the partial charge on these phosphates? Positive. Why is it positive? It has no formal charge. That's positive charge because oxygens are much more electronegative, right? So we have electronegative oxygens all around this partial positive charge. Positive charge there. And you can see you have 2 partial positive, very big, bulky atoms, partially positive. In fairly close proximity. It's not very favorable. Cleavage of this bond reduces electrostatic repulsion. Electrostatic repulsion. That's probably a better word instead of saying unfavorable and negative. Electrostatic repulsion. That's probably a better word. Use that. Electrostatic repulsion between 2 partially positive species that are large in close proximity. Separation of this electrostatic repulsion is favorable. Second, the idea of charge stabilization. This kind of goes hand in hand, doesn't it? We just talked about if we have partially positive charges, it's going to be stabilized by negative charges. And if we want to shield this partially positive charge, it's more shielded in its dissociated form after it's being fluid in its hydrolyzed form. It's more stable, so we can compare shielding positive charge phosphates are stabilized by more negatively charged species in our products versus our reactants. The third effect we'll talk about is resonance stabilization. And no, we're not going to spend a lot of time on this. Resonance stabilization. Man, if we were in 1441, we could spend a whole day drawing resonance structures for these phosphates, right? And we're drawing resonance structures for ATP. I want to do that. That'll be fun. We can get a worksheet going on. If you took it here, you don't find that, right? Because we did these worksheets. Yes. That's fine. Y'all ready? That's where your whole exam's going to be over. Resonance structures of ATP. Most of you would probably be excited. Yes. Do this. No. Resonance stabilization. It's pretty obvious. You could draw resonance structures. How many resonance structures do you have for let's just look at this phosphate. How many resonance structures? How many good resonance structures do you have? 3 for this phosphate right here, right? We have 3 equally good resonance structures. How many equally good resonance structures do we have? And you know what? Let's forget the rest of ATP. Let's just look at the structure right here. Our 2 phosphates. Our 2 terminal, our beta, and our gamma phosphates. Around this, how many resonance structures do I have? How many good? I have many. You do have many resonance structures. How many good resonance structures do you have? What? 4? Where would my 4 be? If I drew 1 right here, where would be another good resonance structure? The opposite, so I can take these double bonds and move them down. Give me another good one. 1 flipped up, 1 flipped down. Are those equal at that point? At that point, they wouldn't really be equal, right? I actually don't know which one would be more stable or which one would be not. So let's assume they are equal. Then that would give me 4 resonance structures, right? So I could possibly, if they are equal, which I honestly I don't know. If they are equal, actually they would be equal, wouldn't they? They would be, because those are, what's the geometry around these? Yeah, they would be equal. So we would have a problem. Actually, I don't know. I'm starting to think now they wouldn't be equal. But I don't know. Let's assume they are. So that gives us 4 total good resonance structures, right? 4 total good equal resonance structures. We assume they're equal. But I already have 3 here. How many resonance structures do I have here? 3 more, right? So I have many more resonance structures. This is much more resonance stabilized in my product over my hydrolyzed ATP into inorganic phosphate. It's much more resonance stabilized versus our products. And the last one is an easy one. And if you didn't already think of it, you're going to. I should have thought of that. Hydrolysis of ATP yields more products, right? Hydrolysis of ATP yields more products. One thing that I don't know if we talked about last week, I may have hinted on it very briefly, probably did, but we didn't talk about it, is one question you may ask is, we just drew ATP right here and I protonated one of my oxygens and I drew it here and I didn't, I did kind of do that, right? I did say this. So we did talk about it for a second. And I at least said something about it, right? The pKa's of these phosphate groups on ATP, ADP, AMP, inorganic phosphate are the exact same, right? No, they're not the exact same. The pKa's of the phosphate groups on ATP, ADP, and AMP are not the exact same. And I don't care that you know the values, but I do care you know the relative ratios. If you were wondering what is more likely to be protonated, phosphate group on ATP, ADP, or AMP, your guess, the correct answer would be ATP, right? ATP, because as you lose phosphates, the pKa of your remaining phosphate groups goes down. So the pKa of this phosphate here, your last pKa is around 7.7, 7.5. So under physiological conditions, you would expect a noticeable amount. Most of your ATP is going to be protonated, right? For your last pKa, right? If we go to ADP, your last pKa, your highest pKa is around 6.8, 6.7. It's much lower. If you go to AMP, it goes down again, right? So if you're guessing which of the following would most likely to be protonated under physiological conditions, ATP is more likely, or a larger population of ATPs are going to be protonated compared to ATPs and AMPs, right? Now, what about inorganic phosphate? Is it likely to be protonated? Your last pKa? You should say yes, because you know. What is your last pKa of inorganic phosphate? It's high, right? It's high. Very high. 12, right? We said this a second ago. ATP, ADP phosphoryl transfer is not the only high energy phosphoryl transfer. It's not the only high energy phosphoryl transfer. It is the one we'll talk about for the most part. But if you look in your textbook, if you look at tables, if you look at graphs showing high energy versus low energy phosphoryl transfers, you're going to see ATP, ADP, AMP on the list of high and low energy phosphoryl transfers. They won't be at the top of the list, they won't be at the bottom of the list. And if you forgot from last week, I asked you to look up the effects of metals on ATP hydrolysis. Hopefully you did that. And if you have not done that yet, please do so. I probably won't ask a quiz question about it, but I guarantee you will be asked an exam question about it. So that is something we should have done. Okay. All right. So just as important as phosphoryl transfers, another mechanism of action in biomolecular processes, just as prevalent, just as important, if not more important, are biological redox reactions, so oxidation reductions, reduction reactions in biological processes. I told you today we are wrapping up chapters 3 and chapters 17. And on Wednesday we will start with glycolysis. We will start with glycolysis. We will start with glycolysis on Wednesday. I'm excited. 5 pathways that we've done. Next, are y'all excited? I found some. I have some news. This is hearsay that I'm going to share with you. I'm not even not. This is the hearsay. I heard through the grapevine that I'm not going to be teaching about it. I want to take about next semester. I don't know who is teaching it, but I was told that most likely it is not going to be me. I don't know. I do what they tell me to do. What?
Next fall, maybe?
I have no idea. And I still don't know about in spring. I still don't know in the spring for sure. But I heard that I'm not taking it. So I apologize. I don't think you got a lot of options because I don't think there's one section. Have y'all registered yet or no?
There's only one section?
I think that there is only one? That is true, right? I heard there was only one section. Okay. No, I heard there was only one section, so I do believe that to be true. And I also believe it's true that I am not going to be able to teach it. I would like to teach it, but I don't know who's teaching it. Here are my guesses. It could be Mandel, it could be EO, or it could be Johnson Winters. Those will be the other 3 options. I guess there's not, so coupled with them, I am the other biochem professor here, and what's up? What? No. They're all fantastic teachers. I've had them for various classes. I've talked to them. I've hung out with them. They're on my committee, so I've talked to them about a lot of biochem. They all have different areas of expertise, but they're all very, very smart people. Sorry. I'd like to teach biochem. Not this semester. If you hold your breath and you wait, you ask, what about next fall? You can hold your breath, I don't know. We'll see. I hope I get to teach it. Don't hold your breath. You wouldn't do that. We're going to talk about cellular respiration. It's not the same thing. That was a bad joke. That was stupid. That was very dumb. That was worse than a palindrome. Okay, redox reaction. What should you be able to do? You should be able to, in this, so much of this is you should be able to identify redox reactions, oxidation reactions, reduction reactions. So what do we mean by oxidation? a loss of electrons, right? A loss of electrons. This is represented. You could represent this as a redox pair or redox couple. Frequently, you will see a typical oxidation reaction. If we're talking about the oxidation of iron, is the loss of electrons. So if we're losing an electron from an iron 2 cation, you'd be left with an iron 3 cation plus an electron. And this would represent the oxidation of iron. Right. What's up? Shouldn't there be two what?
Never mind.
We're not oxidizing iron solid iron. It should be an oxidation of ionizing. You look at copper. We're looking at the reduction of copper, right? So the oxidation of copper would be the loss of an electron. Reduction would be gaining an electron. So the reduction of copper, copper 2 plus an electron going to copper 1 plus. And these are often written as concerted reactions. So the oxidation of one species leads to the reduction of another species. So I could write this same reaction as flow of electrons from iron to copper. Leave us with an oxidized iron. Reduce copper species. Pointless. So frequently you will see the phrases redox pair, redox couple. And it is talking about the flow of electrons between iron 2 plus, iron 3 plus, or copper. In many biochemical reactions, the flow of electrons is also paired with the flow of electrons or loss of electrons is also paired with the loss of a hydrogen ion. So dehydrogenation is a term that tells us that loss of electrons paired with loss of hydrogen ion. This happens in an enzyme. We call this a dehydrogenase. Dehydrogenase enzymes pair loss of electrons with loss of hydrogen ions or hydrogens. We'll talk in a second about where do these electrons go. We need carriers, we need facilitators, we need transporters of electrons. We'll talk about certain coenzymes that act as electron shuttles or electron carriers. You see electron carriers. It's pretty indicative of a redox reaction, right? If electrons are moving, you need something to move those electrons. So when we talk about things like NAD, FAD, NADP, those are redox carriers, electron carriers. You'll see these dehydrogenases. So if you see any enzyme mechanism of the dehydrogenase and they don't show you electron carriers, you know that they're liars, right? A bunch of liars. So what do we mean by dehydrogenation? Dehydrogenation reaction. Be an oxidation paired with the loss of what?
Hydrogen.
Hydrogen, right? So we have an oxidation paired with the loss of hydrogen. You know what? I'm going to go ahead and write this. Let's pretend like we knew we lost hydrogen, right? We knew we lost hydrogen. We look at our reactant, we look at our product, we see a different number of hydrogens, right? How do I know that I lost 2 electrons? How? We broke a bond. So I know I lost some hydrogens because I broke around. How many hydrogens though? I know I lost electrons because I broke. How can I count those electrons? You did this in organic chemistry, didn't you? I hope you did this in organic chemistry. How do we count oxidation states on carbon? Carbon-carbon bond. The oxidation state on the carbon is 0, right? Why? This cleavage of a carbon-carbon bond, what would you expect those electrons to do? What kind of cleavage do we call that? Right? So these are terms you should have learned in organic, right? Homolytic versus heterolytic cleavage. A CH bond, we give a charge not of +1, of -1. Why? Because our electron stays with our carbon, right? Why? Carbon is more electronegative than hydrogen. CR, where R is oxygen, phosphorus, right? R could be oxygen, nitrogen, sulfur, phosphorus to some degree. You would give it a charge of +1. Why? Because carbon is considered less electric. So if we take our same system and we just you could count our oxidation states on this carbon. And if we want to know if this is an oxidation reaction or if we know if this is a reduction reaction, this is something you're going to do on your exam, I promise you. You're going to have to track the oxidation states of both species. So my oxidation state here, my carbon-carbon bond, 0. Carbon-hydrogen bonds are -1 each. What would my oxidation state on this carbon be? -3. Same thing here, carbon-carbon is 0. Carbon-hydrogen is -1. Carbon-oxygen is +1. What would my oxidation state on this carbon be? -1. Right? After my reaction, does this carbon change? No, still -3. Does this carbon change? Yes, it does. Now it has 1 carbon-hydrogen bond, 1 carbon-carbon bond, and 2 carbon-oxygen bonds. So my oxidation on this +1. What can you tell me about the number of electrons? I lost how many? 2, right? I went from -3 to -3, which is no change. I went from -1 to +1, so I lost 2 negative charges. I lost 2 electrons. So if you have no idea how in the world we came up with this, it's a 2-electron oxidation. You need to be able to count oxidation states, what's changing. So you can compare oxidation states of your reactants to oxidation states of your products. And you can see that, well, calculate my oxidation state, I lost 2 electrons on that part. So this would be a 2-electron oxidation. And how do we represent a 2-electron oxidation? I say +2E minus. So you may see that both ways. You may see it written as a sentence. This would be called a 2-electron oxidation. Right? 2-electron oxidation. If I said a 2-electron reduction, I'm adding 2 electrons, right? If I said 2-electron oxidation, I'm removing 2 electrons. Lastly, a small precursor to what we're fixing to be doing. NAD, FAD, NADP. Yes, thank you. NAD, FAD, NADP. These are some of the coenzymes that we're going to be talking about in our various pathways that we're fixing to be doing. These are coenzymes, and they have one purpose, and they're one purpose to carry electrons, to shuttle electrons towards, away from redox reactions. They take electrons towards reduction reactions that shuttle electrons away from oxidation reactions. Both oxidation and reduction are occurring in the same enzyme. They can take electrons from one place and deliver them to another place in the same enzyme. Do some neat things. If we look at NAD, what does the oxidation and reduction of NAD look like? So this is, if we look at NAD plus let's see.
So if I'm adding 2 electrons, this is a 2 electron reduction, right? It's not a 2 electron oxidation, it's a 2 electron reduction. So if I'm going from NAD plus to NADH, that is a 2 electron reduction. From NADH to NAD plus, that would be a 2 electron oxidation. By the way, right? 2 electron reduction from NAD to NADH. So which form is my oxidized form? Oxidized form is my electron deficient form, right? You lose electrons in an oxidation. So my electron deficient form is my left-handed or right-handed form? Left, right? So this is my oxidized form. My reduced form. You can see that as your electron rich form. So if I'm going from a reduced form to an oxidized form, this is called reduction, right? So if I'm going from NADH to NAD plus, that is a reduction, correct? Yes. The answer is no, I can't screw that. But I can move the camera down. That works. Going from NADH to NAD plus is a reduction reaction. I wrote that wrong. Is an oxidation. I had one job and I got it wrong. One job. I didn't do it. That is an oxidation. Nobody said anything. I said it like 6 times. Who was thinking it? Oh, everybody was thinking it. Everybody just let me sit here and look like it. I appreciate it. That is a 2 electron oxidation, right? Because we're losing 2 electrons. And going from NAD to NADH would be a reduction. We said a second ago, NAD, NADH, maybe talked about as a redox couple or redox pair, right? The reduction and oxidation between NAD plus and NADH, NADP and NADPH, FAD, FADH, this redox couple. Has a reduction potential minus 0.320 volts. What do we mean by reduction potential? What do we mean by positive or negative reduction potential? A negative reduction potential negative reduction potential means it is a good reducing agent. A negative reduction potential means it's a good reducing agent. It's good at reducing things. A positive reduction potential means it's good at oxidizing things. So molecular oxygen has a very positive reduction potential. Molecular oxygen excels at oxidizing things. A negative reduction potential means it's good at reducing things. And we'll talk more about redox reactions in our first couple steps of glycolysis. The last thing I want to talk about real quickly, and again, I hate on biology majors. I hate on biology majors because you should know this stuff. So I talk about a few terms when it comes to metabolism that you should know. Let's go over a list of things that you should know. You may not see these directly on your exam as a question of what is anaerobic versus aerobic respiration, but you'll probably see questions where if you don't know the difference, you probably don't know what the question's asking. So, you should know the difference between an aerobe and an anaerobe. Aerobic respiration versus anaerobic respiration. Yes. You should know the difference between an obligate or facultative anaerobe or aerobe. You should know the difference between an auto or heterotroph. Photo or a hemotroph. Again, for most of you, this is probably stuff you've seen multiple times. When we talk about metabolism, these are terms that we need to talk about. Pathways of metabolism, the type of organism. What does that organism utilize? Can that organism fix carbon dioxide? Can it fix inorganic materials? Because if so, that's pretty unique. If it can't, then it needs extra carbon sources. It needs to eat things. And it needs plant material. It needs organic material to eat. Metabolism, the last thing I'll talk about metabolism. Metabolism is utilizing nutrients to do something, right? And utilizing nutrients, breaking down of nutrients, building up of nutrients to make things. And the difference between anabolism and metabolism is just that. Anabolism is also known as biosynthesis. So anabolism is synthesis. Synthesis. Metabolism is degradation. So we have synthesis of macromolecules. From small components. Metabolism is the reverse direction, the degradation of macromolecules into smaller components. So anabolism is synthesizing lipids, polysaccharides, things that we need. Metabolism is breaking those down into smaller components so that they can be used for other things. Two words that really help describe these processes, and it's not because I like the movies, but I did like the movies. Anabolism can be seen as something that is divergent. Don't laugh. I'm a hipster. I'm not a hipster. Catabolism is something that is convergent. What do I mean by this? Anabolism is divergent. You take a few large complex molecules, proteins, fatty acids, and you break. I just said that backwards. Divergent is something completely different. You take a few end products, a few small molecules, and you can build many different big things, many big different proteins, many big different sugars, big different fatty acids. Catabolism is the exact opposite. You take many big end products and you basically break them all down into the same three things: ammonia, sugar, water, and carbon dioxide. There are 3 stages of catabolism. We'll talk about those at the very beginning of the next class. And we'll start with glycolysis.